So now it's time for the last keynote talk from Professor Christos Cassandras. Christos, if you want, you can start sharing your screen. All right, yeah, I see it's nice. So again, another difficult task to introduce a speaker that has done so many things, but I'll try. So Christos is a distinguished professor of engineering at Boston University, where he is the head of the Division of Systems Engineering, and also professor of electrical and computer engineering. And he co-founded the Boston University Center for Information and Systems Engineering. Now, something about him: he studied at Yale, Stanford, and Harvard. He was working for a while with ITP Boston, and he was also faculty at University of Massachusetts Amherst. And his research specializes in discrete event and hybrid systems, cooperative control, stochastic optimization, and computer simulations, with application mostly to computer and sensor networks, manufacturing systems, and transportation systems. So definitely Christos is one of these people we were talking about before that have the foot both in the robotics, control, computer science, and transportation systems fields, which is great. Of course, he has published a lot of interesting works on the subject and won several awards. And today he's going to give a talk about optimal management of mobility on demand systems. I'm following this work by his lab, and I'm really excited to hear more about it. So Christos, go ahead and tell us more.
Okay, well, thank you very much. I'm taking this opportunity to thank you also for the organization of the workshop. I've learned quite a bit, and one of the things that I have learned from listening to the talks from the very first one until the last one is that this whole issue of how to deal with transportation systems and particular mobility on demand systems can be done at very different levels. So starting with the very first talk, where we saw that you could look at problems at the level of how do I assign vehicles to various users, all the way to how do I do pricing, how do I do rebalancing, so on. And then throughout the day, people have been talking about the management of mobility and demand systems at different levels. My main focus in this particular talk is at the lower level, the level at which I really want to, hold on, because oh, there we go. I assume that you can see my screen with the map. So what I wanted to say is that I want to focus at the level of ride-sharing systems, where the key problem is how to get these vehicles participating in a fleet to cooperate so as to do the best we can to assign the proper vehicles to the proper users, with the two goals that you see here at the bottom: minimize the overall passenger waiting and traveling, and through the cooperation also to minimize as much as possible the traffic congestion that we know all these fleets of ride-sharing systems can add rather than alleviate from the transportation system. So this is just a typical kind of simulation, just to indicate my color convention and symbol convention. The green vehicles are the idle vehicles moving around looking for a ride share. The red vehicles are the busy ones, and you also see occasionally this little triangle showing up, which indicate where new user requests come. So as I said, I'm going to focus mostly at the level of how do we assign vehicles to users or users to vehicles, and then at the very end I'll make a few additional comments of what we can do at a higher level. In other words, I'll take the point of view of the user here. What's the best thing that we can do for the user, rather than worrying about things like welfare maximization if you are a community that's trying to accommodate this type of ride-sharing systems, or profit maximization if you are a provider. So a quick literature review, by no means complete. The thing that I want to point out is that when it comes to optimal assignment problems, this is a very well-known problem. It is generally computationally complex, and there's a lot of issues related to the combinatorial complexity of the problem, of any assignment or scheduling problem, and also to the problem of how do you model uncertainty? What is the right choice to be used? And here I mentioned just a few of the types of approaches with representative papers. There's re-optimization approaches where every time something interesting is happening, you try to resolve the problem. There's model predictive control approaches. There's dynamic programming approaches, which we know to be plagued by the well-known curse of dimensionality, various heuristics. And what I will try to talk about today is a receding horizon control approach, which is event-driven. So in that sense, it's probably closer to the MPC way of looking at these kinds of problems, but the emphasis here is going to be on the event-driven part and how that can really lower your computational complexity by orders of magnitude. Okay, so here's the basic problem formulation. It is a stochastic optimization problem because we don't know what the demand is. We don't know what the traffic conditions are that will affect travel times, but basically what we want to do is we want to minimize, again, remember I'm looking at it from the point of view of a user here. We want to minimize some kind of combination of waiting time and travel time, meaning once the user is in the car, and we weigh those two components with an appropriately normalized weight choice. So we have a convex combination. What is the control here? Well, the control is a destination vector of all the vehicles that participate in this fleet. And I will try to specify that. So in the picture that you see, we immediately realize that even though we'd like to work in a graph topology here, it's not really a graph topology because aside from the points in the graph that is defined by a map, we also have segments where we really would like to keep track of where the various user requests come and the drop-off points. So the pickup drop-off points indicated by these arrows, which must be dealt with in a real line segment. So it's really a mix of a directed graph topology, sort of a map topology, and points on the map which lie between, on links essentially, which we would like to keep track of. So we'd like to use a Manhattan distance metric as opposed to a Euclidean metric. I remember in earlier talks, people talk about using Euclidean metrics as approximations, which is fine, depending on the level that you're looking at. But at the level that we're looking at, we need to be reasonably accurate. So what is the system state? If you really want to define this as I point out here, a event-driven system, meaning a system really where all the essential dynamics are governed by specific discrete events. So first of all, you have a set of vehicles. These are the vehicles that are participating in a fleet at any given point in time. I'm pointing out that this is time varying because you may have vehicles that come in and come out of the fleet at will. For each vehicle, there's a certain vehicle position, and for each vehicle, there's also a certain content and number of passengers, an integer up to a certain capacity that indicates how full or not the vehicle is. And then you have the other side of the coin, the passengers. You have a passenger set at any point in time, and the state of the passenger, or what I sometimes call a user, could be 0, meaning that the passenger is waiting, or the passenger has already been assigned to a specific vehicle. So this is associated with a particular index J that would fall in the vehicle set A. Finally, if we're to model waiting and traveling times, we need an additional state variable for each passenger, which I refer to here as a clock, which represents the time that the passenger has waited until they get picked up, or traveling time inside the vehicle. So all these transitions pertaining to this state are driven by 6 event types. And here they are. First of all, you have an event called here alpha I, which is a service request issued by passenger I, a new request for a ride. Or you can have a beta J event, which refers to a vehicle J that joins the mobility on demand system, or gamma J when a vehicle leaves the mobility demand system. So this is what's going to affect the state of the vehicle set. Then we have a pi ij event, which is a vehicle representing the event where, which is an event that represents a vehicle J, which picks up a passenger I at a particular point in time in my sort of mixed map an Euclidean segment topology indicated by OI. You have another event, which is a drop-off event. And finally, you have an event where a vehicle happens to arrive at one of those nodes in the map where it can make a decision to reroute, to go straight, turn left, turn right, potentially even, I guess, U-turn, in order to decide which way to go. So this, in sum, is the set of events that change the state of the system. And the whole idea of this event-driven receding horizon control approach is to perform the following function at each event: control or uncontrolled. First of all, calculate a certain planning horizon. So over what period of time do I want to make decisions? Then solve an optimization problem over that particular planning horizon, which gives you the optimal vehicle assignments over this horizon. Then execute that solution, the optimal solution, over a much shorter, generally, action horizon, little h, and then repeat. Now, here's the distinction between the conventional time-driven receding horizon control, what we typically do in the model predictive control setting, unless it's already been adopting the kind of more recently developed event-driven techniques. So in a time-driven way, you determine a planning horizon, you solve a particular problem, which gives you your optimal control over that horizon, and then you execute it for a typically small time step. Then you repeat over another planning horizon, you execute, and so on. And notice that in this approach, the time steps are fixed, and the decisions are made at the end of each one of these time steps. However, in an event-driven context, everything can be done asynchronously. So an event, you wait until an event occurs at some random time or pre-calculated time, and then you make another decision, and then you execute that decision until the next event occurs here, and so on and so forth. And notice that this gives you a lot of flexibility, because if nothing interesting is happening over a particular period of time, there's no need to go back and recalculate and resolve potentially long and tedious optimization problems. You just wait until the next interesting event. Plus, you accommodate the reality of the real world, which is that things change in an asynchronous fashion. So the key questions then, if you're going to operate in this particular fashion, is to decide what is the planning horizon and what is the action horizon. Well, in our case, the planning horizon turns out to be the estimated time until the next passenger pickup or drop-off event occurs. Why do we choose that? I'm not going to go into details, but if you do a particular analysis, which was done some years ago for these types of problems, this provides some stability or some guarantees of stability to your system. As for the action horizon, it's really easy. You just wait until the next interesting event occurs. For example, you wait until a new passenger request occurs. In between, there's no reason to change anything regarding your control. So how do you solve now the optimization problem once you pick the planning horizon, which is this capital H? Well, the optimal decision, or the optimal control in this case, which remember is a vector of where each vehicle goes in this map topology, consists of a immediate reward, and then of an estimated future reward. So basically, this is a dynamic programming problem, but we're going to simplify it by estimating the future rewards after the planning horizon is expired in a particular way. But the key difficulty here is the huge dimensionality of this action space. It's too large. At every point where K, which is an event occurrence, it's too large a set in order to try to determine what the optimal solution is. So what we do is reduce this by defining a much smaller set of possible choices, which is referred to as the active target set. And this terminology has been inherited from when we were solving problems in this way in the uninhabited air vehicle time, where these things became very attractive, a lot of military applications. So target was the right notation or terminology to use. For target, now you can think of were passengers. Okay, so let me explain what this concept of an active target set is. If I go back to Euclidean space, and I want to solve what is essentially a dynamic programming type of a problem here, at any point in time when a decision has to be made, once a planning horizon has been determined, your choice is really to go any point on this circle, whose radius is defined by the planning horizon, times the speed at which this particular agent moves. And so you can see that I have an infinite dimensional space. I have to decide where the best place to go on this circle is. Now, in this particular case, I have a set of potential target points. And the way that I define my planning horizon, my radius here, or my planning horizon, always includes one of the targets, the closest one, to be on this circle. So if I were to solve this particular problem with, how many do I have? 6 possible choices here. I have to solve an infinite dimensional problem to tell me which is the best point on this circle to take my agent and move to. But I don't have to, because there are some agents which are simply too far away to worry about at this point. So the way to define this smaller and finite set of active targets is to break down the infinite set of points on a circle into a finite set of sectors defined so that each sector is associated with one target closest to them. So for example, this blue sector over here is defined as being associated with this particular target point Y2, because it turns out that any point that I go to in this blue sector gets me closer to this particular target than any other point. And this allows me to eliminate some target points like this one and this one, which are too far away. And of course, you see here, this red sector indicates that any point on this sector is associated with this particular target. So this allows us to reduce the infinite dimensionality of an action set defined by a circle into a finite set, which in this case is defined by 4 points. How do I translate that into a Manhattan distance type of metric other than Euclidean metric? Or if you prefer, the map topology with not only the nodes that are defined on this example grid, but also with the particular points, like let's say this one here, which indicates where exactly on this particular arc on this graph is a particular, for example, in this case, destination of the passenger coming from. So if I have a vehicle now in this particular topology, vehicle J, which is located right here, I can immediately see that once I define a planning horizon, this can take me to a set of what we call horizon points. This is about as far as I can get, points 1, 10, 9, etc., using my planning horizon. And so you can see that if the planning horizon is HK, if I wanted to get to target 2, which in this particular case happens to be the origin point of it's a pickup point, I would have to follow this particular path. And these are called horizon points. So this is again a copy of a map, and applying this same idea of a target set, I can reduce the set of all the possible target points here. In other words, all the possible pickup or drop-off points, pickup points being the squares, drop-off points being the triangles. I can reduce that, as it turns out here, with a much smaller set that comes from the topology. And then, if I want to solve a problem like this, this means that rather than having to look for all the possible destination vectors of all of my agents here, all of my vehicles, I can reduce that to a much smaller one. In this particular example, it would be points 9, 5, 3, and 1, 9, 5, 3, and 1, because these are the closest ones to the particular pickup or drop-off points that I access. For example, if I'm interested in a decision which will take this vehicle to go and pick up a passenger at this location 4, then the planning horizon point is this point 1 over here. So this leaves only, now that I've identified my action space, the issue of how do I define in this particular equation the immediate reward and the estimated future reward. Well, the immediate reward is fairly easy to identify because it depends on whether the planning horizon that we have identified here includes an event which actually generates some reward. And those events are a pickup or a drop-off. So in this particular case, it's fairly easy to associate, to define the immediate reward. It's either a pickup or a drop-off reward. my rewards are the waiting time of a passenger or the traveling time of a passenger. Rather than minimizing them, I prefer, for various technical reasons, to maximize. So what I do is I define a T, which is sort of like, you can think of it as the largest possible time horizon that I could define, let's say a day, if I'm solving this problem over a day. And so instead of minimizing, I'm maximizing the maximum possible horizon I can think of, minus the corresponding benefit, which is the waiting time. Estimating future rewards becomes a little trickier because we have to make some assumptions and estimate the reward accordingly. Helpful in this sense is defining something that we call the travel value of a passenger I associated with vehicle J. And the travel value of this passenger is related to how long the passenger has waited. So if a passenger has waited very long, you want to give his travel value a large value because you get a big reward. You will reduce that waiting time by a lot. And also, you want to take advantage of what you know about the topology to look at the shorter possible distance between a passenger and the associated vehicle you're trying to schedule, and you give a much larger value to those passengers that you can pick up quickly because they're close. So based on the travel value, we can determine an order sequence of future passengers, what I call targets early, to be visited. Here, I'll spare you a lot of the technical details, but this is the formula, if you will, or the estimate of all the future rewards, which depend on a sum of all of the immediate rewards, where I have defined this sequence, this ordered sequence of future passengers to be visited. I have defined an order. I have defined the time to each target, and there's a discount factor, which simply indicates that if you're trying to predict how long it's going to take you to get to a target, which is way into the future, the accuracy of that estimate is, of course, going to be much smaller. So given this, I can solve this optimization problem, which includes my immediate reward, and it includes all of the estimated future rewards. The important thing to notice is that the optimization problem is simply over a set here, which is that reduced number of possible pickup or drop-off points to visit, defined by these active sets. And of course, it's over the set of all the vehicles. This is not necessarily a very large set. This, I have already told you that it's reduced. So essentially, this is a problem that can be solved by exhaustive enumeration. You simply evaluate what's in this bracket. Of course, there's some computation to be done here, and simply pick the best next destination in order to achieve that. So this gives you a sense of the complexity of this problem if you did it by exhaustive enumeration. This gives you a sense of the order of complexity when you adopt this reduced active target set. And just as an example, if you have 5 vehicles to assign passengers to, and there are 10 passengers that are out there, the exhaustive enumeration, it's a scheduling problem, no surprise there. It's of the order of 10 to the minus 4. Using the receding horizon control approach, the complexity is, I don't remember the exact number, but something less than 50. So you see a reduction from 10 to the 4th to something like the order of 10. So a 2 to 3 order of magnitude reduction, which is substantial. Let me close with a few simulation examples here. These are simulation examples from a 10 by 10 map or block map, 10 by 10 blocks of the New York City map. This is based on actual data of New York City traffic. I think this is something that many of you are familiar with. You can find in the web. In this particular example, we used a fleet of 28 vehicles, a horizon in time of 160 passengers to be served, and we assumed that the vehicle capacity was 4. And this is a sample of the results that we got in terms of waiting time and traveling time for different weights in terms of waiting versus traveling. So in this particular first row, we paid more attention to the traveling. We don't want to have people wait too long in the vehicle itself. And this is also another metric of efficiency, which is the vehicle occupancy. As you can see, is between 2 and 3. Remember, the capacity was 4. Now, an obvious question is, okay, all right, so you give me some results, but what am I supposed to compare it with? Actually, this is difficult to do because there really aren't a lot of methods that we found in the literature that solve these problems and have results that have been posted out there. So what we found as a good baseline for comparison is a particular greedy heuristic, which was published in this particular paper. And as the term indicates, it's a greedy heuristic. It simply goes essentially to the closest possible pickup and tries to accommodate the passengers there. And this is a comparison. And what you can see is that the receding horizon control approach with this very significant computational complexity reduction essentially reduces the waiting time on average by a factor of 3, the traveling time by something like 20% or so. And this is the weighted sum. So again, you see it's a factor of 3. So it's a significant reduction. But again, there may be other algorithms that people have developed and that we're not particularly aware of over the last 2-3 years. But this gives you a sense of how this works. The histograms that you see here give you a sense also of how the waiting times and the traveling times, waiting times here, traveling times here, are distributed. So you see, and this is what you like to see, is you like to see the algorithm that you use basically favoring short waiting times here, as opposed to very long waiting times. So the greedy heuristic, for example, has a lot of passengers that wait more than 17 minutes, which is pretty high. And so we skipped all the enumeration here of 18, 19 minutes and so on. And in the traveling time, you see a similar phenomenon where the traveling time is concentrated in the 2, 3, 4, 5 minute range, as opposed to the 17, 18 minute range and above. Okay, so let me conclude briefly by just saying what this particular piece of work has done. It has concentrated on modeling ride sharing for on-demand mobility systems as a event-driven dynamic system. Then we concentrate on solving optimization problems that favor the passengers, not the fleet, not the community, which is just one way to do things, and show the advantages in terms of computational complexity of this technique of event-driven receding horizon control that we have used in other contexts in robotics and other multi-agent system problems. The benefits, performance, I don't know if this is exhaustive, but we've compared this particular technique to various greedy heuristics that we found in the literature. And then finally, there are some open questions. For example, where do you position idle vehicles when there are idle vehicles so that they're best used upon receiving future calls? This can be done by obtaining some historical data of where it's more likely to find your demand. What if the destination information is available? The analysis that I showed you assumed that when somebody is making a request for a ride, they do not provide destination information. If you did, it's not hard to extend what we just did by augmenting what I call the travel value function, so that if you know where the destination of that passenger is, you can include an additional term which makes the travel value function a little bit more descriptive. Again, this was a lower level assignment problem solution, which takes a user-centric point of view, not a provider-centric point of view. So what if we want to take a provider-centric point of view? And of course, something that we've heard repeatedly in earlier presentations today, what about the extra congestion that may be due to this mobility on demand systems? I started out my talk by saying that part of what we wanted to do is enhance the cooperation of vehicles by having them talk to each other so they arrange their destinations in accordance with the cooperatively shared information, but this remains an open question. And so just to show you that we have not neglected the higher level points of view of provider versus user-centric approaches, this would be a picture that gives you more of the provider-centric approach. You have a fleet of vehicles here at a particular location, and you have your demand here. And so when a new passenger arrives, you'll have to make a decision. as to whether you want to accept the contract offered by the provider. You may lose some customers because they find that the cost is too high, the price is too high. You also have capacity constraints, so you may lose another part of your demand because you don't have enough vehicles at this location, which makes the rebalancing problem really interesting. But once you pair up a resource, a vehicle, with a user, a passenger, then you send them over some delay, which depends on the topology and the traffic conditions, to their destination, and of course the process repeats. So there is a profit maximization problem formulation, and there's a welfare maximization problem formulation. I simply wanted to give you these formulations here. I'm sure that many of you are familiar with those, and some may have even dealt with these problems. And the reference below is a very recent paper in which we dealt with the autonomous mobility on demand systems at that level. And in fact, in this particular case, just like some of you already talked about, we consider the issue of intermodal mobility, where your passenger may choose to use their own private vehicle versus their a shared vehicle or public transportation. But that's a whole different piece of work and requires a different perspective. So I'll stop here. And again, thank you very much.
Thank you, Christos, for the great talk and also the insights on these next works you're planning to do. Let's see, are there any questions from the speakers? People in the audience are quiet. I don't know if it's because it's late or what. Actually, I have a question. So I have a couple of questions, but this one is a particular. Oh, we see the dog now. Yes. So it's a particular question. So you said you haven't found a lot of works dealing with the same kind of problem, and we recently made a large literature review for these kind of problems, and I think the reason might be because you're solving many problems at the same time, right? And my question is, have you tried to put these algorithms in place into other networks, or how would you see these being implemented, for instance, by some routing companies or by some ride-hailing companies? So do you see this really as a potential alternative to those algorithms?
Yes. So I think in one of the earlier talks, I think just before the long break, we talked about modularity. Is it possible to kind of modularize a lot of these problems and solutions that we each offer? Because many of us as researchers, we kind of tend to pursue our own little problem. We solve it, we're happy, and then we say, well, it's up to you, world, to just go and use my technique as best you can. I think this remains an issue for this particular area, but this particular algorithm, I think, is kind of a plug and play algorithm, because if you look at the basic starting point with this event-driven point of view, it makes it very easy for a provider or whoever, maybe a community or community adopting, let's say, a community-based public TNC type of, not TNC company, but a TN service, because it's just a bunch of events. So as long as you have the network infrastructure to record on your smartphone, whether there's a new request, whether there's a pickup or a drop-off, and whether there's a new vehicle that joins the service or leaves the service, the rest is just a black box that we're providing. And so in that sense, I think this is a plug and play module.
Okay, great.
The event-driven point of view is important in this sense. Not only for that reason, but also if you notice, it takes away the need for accurate statistical or stochastic modeling. For simulation purposes, of course, we generate the demand according to whether it's Poisson processes or other processes. I generally tend to favor the doubly stochastic Poisson process, so I can generate perhaps some, bursts in the demand, so you can have little bursty demand. But it doesn't matter, because whatever the model that you use is, the algorithm doesn't care about.
Yeah, exactly. That was my, you perfectly connected to my next question, which is I wanted to relate a bit what you talked about and what Faye talked about in the first part of her talk when she was dealing with these distributions of potential demands.
That's very useful too, because if you gave me a better idea of potential demand and forecast demand, of course I can use that. For example, in one of my open questions, where do I place the idle vehicles? If I have a good idea of where the demand is coming from, or where it's coming from over the next hour or so, of course I'll use this information. So any kind of learning type of technique is very essential.
Very cool.
I guess one of the things that's emerging from here is that we're all working on different aspects of the same problem, but it would be nice if at some point we could all have, a big sort of a gala event and just plugged in all of our ideas together and created the huge sort of panacea for all the problems in intelligence.
Yes, that would be great. I agree with you. But yes, we
can afford to dream a little bit.
Exactly, like there is a spectrum before to get there, and I think even standardizing some of the comparisons and so on would be great. Any other question from the speaker list? We are a bit ahead of time. We have 5 minutes earlier. Doesn't seem so. Let me check again the document. Nope.
Okay.
Thank you very much, Christos, again for your time and for the great talk. And good luck for the next endeavors.